Welcome to Cactus 2. This tutorial covers the basics of the component editor. Click the New File button to open the dialog for creating new documents. Here we can change the hierarchy and firmness of the new component, as well as create identifying tags. Tags can be used to group different documents together. The library of Cactus 2 allows filtering using the desired tags. Click the plus button to add a new tag. This component will get a tag identifying it as a tutorial component. A tag can be given a color to better identify it. You can remove a tag by clicking the Delete Tag button. Hit Enter to finish the tag. A new component needs a unique VLNV. The revision selector allows you to choose the IP-exact revision that this component uses. Directory shows the target path where the XML file of this component will be saved to. The default path is the current default library path of Cactus 2, appended by the VLNV of the new component. After creating a component, it can be found in the library. To further refine the new component, Cactus 2 launches the component wizard. The first page allows the editing of the general information for the component. Next is the editor for file sets. The Import Source File page lets you import a top-level file into the component. For further information on importing a file, please see the related tutorial. This page also allows the editing of component ports. The port editor will be explained in detail later. Views page helps you set up the views for the component. Views can be added, removed, and edited here. The last page shows a summary of the configurations made during the component wizard. Click Finish to finalize the wizard and open the component editor. In this part, we will introduce the component editor. The component editor tree is shown on the left side of the editor at all times. It displays the different sub-editors of a component. Selecting an item opens the specified editor. In this tutorial, we will be focusing on the following editors: General, Choices, Parameters, File Sets, Memory Maps, Address Spaces, Instantiations, Views, Ports, Bus Interfaces, Channels and CPUs. Lock governs the state of the document. A locked component cannot be edited. This is the general summary page of the component. It displays the general information regarding the component, such as the VLNV, path, and description. Below these are the Cactus attributes and document tags. These attributes can be used to filter the IP-exact library. A preview image of this component is displayed on the right side. Bottom of the summary is used for validation checks in the component. If everything is valid and working, a green checkmark is shown. If there are errors found in the component, the summary page displays a warning symbol with all the errors that have been found in the component, while the sub-editor displays a warning icon next to it. When a document is saved, Cactus 2 does a validation check and informs of any errors. Click Show Details to display more detailed information of the errors. You can then cancel or proceed with the save. Choices are sets of determined enumerations that the parameters can use to select a value. The Choices editor is divided into two parts. On the left side we have the list of choices and on the right side we have the enumerations editor. Both of these feature the common abilities of the Cactus 2 table editors. Double-clicking in the editor creates a new item. Right-clicking opens up the context menu for the selected item. The menu contains different actions depending on the editor and the context, but adding and removing items are always present. We will create a choice for data width, with enumerations for the possible values. Fields with a yellow background are mandatory. In addition to a value, an enumeration can be given a descriptive text for display purposes. The extra row is removed. We will use these choices in the component parameters. Parameters can be used to control the different variables in the component editor. A parameter has two mandatory fields: a unique name and a value. Resolve determines when the value of a parameter is resolved. There are three options. Immediate is the default value. The parameter cannot be overridden. User means that the parameter can be modified in the configurable element values, but the generators cannot override it. Generator is the opposite of user resolve. The generators can modify it, but the user cannot. Here we can select a choice for the parameter. The available choices are the ones we created earlier. A parameter with a set choice must have a value among the provided list of enumerations. Any field that has the symbol f(x) in its header can receive an expression as a value. An expression can use mathematical functions, as well as parameters. Cactus2 displays the expression in the field, while the calculated result is displayed in the tooltip. While selecting an enumeration, any descriptive text is displayed after the enumeration value. When an enumeration with a descriptive text is selected, Cactus2 displays the text in the field, while the value is displayed as a tooltip. The parameters are now finished, but there is one more thing worth mentioning. Parameter usage count and parameter reference tree. Parameter address width used parameter supported memory in its value. We can observe that this has increased the usage count of supported memory by 1. To further investigate the parameter references, we can open the parameter reference tree for supported memory by double-clicking its usage count field. The reference tree displays a detailed tree view of all the references made to the target parameter. It contains the path to the referencing item, and the expression where the parameter is used. File sets are used to group files together to be referenced by the other sections of a component. The file sets page is divided into two main areas, the file sets editor and the file dependencies. In this example, we will create two file sets, one for Verilog source files and the other for System C files. In order to add files to a file set, we can drag and drop a file from a folder. Cactus2 creates a new row for the file, and updates the file's relative path. We can also manually create a new row and fill in the file path. The editor recognizes both relative and absolute paths. In addition to the file path, a file needs one or more file types. Cactus2 provides a list of the more common types, but a custom type can be given if necessary. The created file sets can be scanned for dependencies. The scanned files are separated by their location, with external dependencies set as unspecified. Dependencies can also be created manually by clicking the field for the starting point and then selecting the end point in the same column. This can be modified further using the Dependency Information sub-editor. The editor for a single file contains details for configuring a file. It also allows options for editing and running the file, as well as opening the file location. These are also available from the context menu of a file item in the component editor tree. These file sets are now complete and ready for use. We will use another component for the memory map example. Memory maps describe the memory structure of a component. In this example, we will focus on the basic building blocks of the memory structure. Memory maps, address blocks, registers and fields. Each memory map must have a unique name and a valid address unit bits value if it contains address blocks or subspace maps. Address unit bits defines the number of data bits each address increment contains. For example, if address unit bits is 32, a 32-bit register would require a single address, 0. If address unit bits is 16, the same register requires two addresses, 0 and 1. If address unit bits is 8, the register uses 4 addresses, 0, 1, 2, and 3. The editor for the created memory map SPI can be opened from the component editor tree. Below the memory map SPI are the memory remaps of this memory map. Memory remaps specify additional memory data used with a selected mode, with the default remap representing the memory map itself. The editor for a single memory map contains the details of the memory map, along with the address unit bits and mode selection. Mode is available for memory remaps, while the address unit bits are editable for memory maps. But the main focus here are the address block editor and the subspace map editor. Each address block is a continuous section of memory within a memory map. Each block must have a unique name in addition to a base address, range, and width. Usage of an address block is selected from one of the 3 options: memory, register, or reserved. Unassigned usage value is presumed to be register if the address block contains registers. Otherwise it is considered to be reserved. The editor for a single address block contains the descriptive information of an address block, as well as definition values and access policies. Address block editor also defines the sub-elements of an address block, registers and register files. A register is defined by its offset and size. It also requires a unique name. Registers can be further divided into bit fields. When a register is created, Cactus 2 automatically creates a single field within it. Fields describe a collection of bits in a register. Like the register, a field is defined by a unique name, offset, and width. This is the editor for a single field, allowing the fine-tuning of its definitions, such as field resets, enumerated values, and access policies. We will create a control register for the control address block. Now that the memory map is complete, we will create a memory remap for it. Memory remaps can be created from the context menu of a memory map. A memory remap needs a reference to a component mode. We will have to create one first. Modes are runtime conditions activated by a conditional port or field. This is the editor for a mode, where we can modify its conditional elements. A conditional element requires an item, as well as an identifying name. The created mode can then be set for the memory remap. In addition, a mode reference must have a priority. When a memory remap is created, Cactus 2 copies the contents of the original memory map. Both of them contain the same address blocks, registers, and fields, and we can see that the status registers are exactly the same. This memory map now contains address blocks, registers, and fields. With the memory visualization, we can see any potential conflicts within the memory structure. The arrows can be clicked in order to display the different tiers. The memory visualization creates an image of a single memory map or memory remap and all its contents. The visualization is dynamic, taking account of any changes made to the memory structure. If an element is out of bounds or overlapping another element, it is displayed in red. Here, a new register is inserted into rec.v buffer. This new register does not take all the space in the address block, so the remaining space is depicted as reserved. Fields are displayed horizontally below the containing register, taking up space determined by their offset and width. With the memory maps complete, we will return to the original component. Before working on the address spaces, we will need new parameters. Address space is a logical addressable space of memory that can be accessed through an initiator bus interface. An address space requires a unique name, an addressable unit bits value, range, and bit width. The addressable unit bits work in the same way as in memory maps. In addition, address spaces can be bound to an initiator interface, which we can see here. This is the editor for a single address space, where we can see the details and definitions. Segments and the local memory map are defined here. Segments allow the dividing of an address space, with each segment starting at an address offset and continuing for a given range. We can observe the construction of these segments in the address space visualization. The visualization displays how the segments align with the possible address blocks of the local memory map. The local memory map uses the same editor for address blocks as a single component memory map, and utilizes the address unit bits of the containing address space. The local memory map is only seen by the initiator bus interface bound to this address space. The finished address space has been divided into segments for registers, data, and peripherals, and the data and register address blocks of the local memory map has been aligned with the corresponding segments. Instantiations are an integral part in representing the different aspects of views. There are three types of instantiations: component, design configuration, and design. Component instantiations describe the details of instantiating a component in a hardware description language. Design configuration instantiation specifies how a given design configuration is associated with a view. A design configuration instantiation requires a design configuration reference, which can be set by dragging the correct document from the library. Design instantiation is similar to a design configuration instantiation, as it defines how a given design is associated with a view. A design instantiation requires a design reference. The editor for a component instantiation contains the identification details, references to the file sets, default file build commands, editors for module parameters, and the implementation details. This component instantiation uses Verilog language, with a module name, core. A reference to the Verilog source files is also added. This is the editor for a design configuration instantiation, which contains the identification details, the reference design configuration, configurable values for the design configuration parameters, and new parameters for the instantiation. This instantiation does not need any editing. The editor for a design instantiation contains most of the same editors. The parameters of the reference design will be modified to use the parameters of this component. The configurable elements editor allows the editing of values with resolve type set as user, but we can also display the values with resolve type immediate. A view describes a representation level of a component. Multiple views can be used for different aspects, such as simulation or synthesis. The view editor displays data regarding deployment and the associated instantiations. If a view contains a design configuration instantiation or a design instantiation, it is considered to be a hierarchical view. The design of a component with a hierarchical view can be opened in the design editor of Cactus 2. For more information on the hierarchical views and designs, please see the design editor tutorial. Ports define the external connection points of a component. This is the summary page for ports. It contains all of the ports in this component, displaying their common attributes, such as the unique name and type. Ports are currently divided into two types, wire and transactional. New ports can be created here, but for a more detailed definition of a port, the port type editors should be used. Wire ports transport binary values, and require a direction and width. Direction can be set as input, output, bidirectional, or phantom. Width describes the data width of the port, and it can be set as its own value, or calculated from the left and right bounds of the port. The wire ports are then completed with a few additional ports. Transactional ports are commonly used for transaction-level modeling. These ports require an initiative, which defines the type of access. This can be selected from the list of requires, provides, both, and phantom. With all of the ports created, we can take a look at the summary page to see them all in one place. Bus interfaces group ports together to form an interface for fulfilling the requirements of a bus protocol. Each bus interface must have a bus definition and an interface mode. The bus definitions can be dragged from the library, and Cactus 2 automatically selects a matching abstraction definition for the bus. Interface mode defines the purpose of the bus interface. There are 7 available modes, 3 standard modes and their mirrored versions, plus a monitor interface. There are errors in the bus interfaces, which are caused by the presence value of the logical ports in the abstraction definition. This will be fixed by mapping the required ports. This is the editor for a single bus interface, which allows us to change the bus definition and the abstraction definitions, as well as add parameters and define the mode-specific attributes of the bus. Initiator mode allows the selection of an address space, defining the range and width for transaction through this interface. The port maps of the bus can be adjusted in the separate Port Map tab. Cactus 2 allows 2 ways to create port maps. You can add rows like in a regular editor, or add all the ports from the abstraction definition using one of the 3 methods. A port map must contain a logical signal connected to a physical port, or a tie-off value. Logical ports with a required presence must be mapped. To connect a physical port to a logical one, you can select a port from the list, drag it from port table, or use the auto connection tool of Cactus 2 to match the ports automatically. Both the logical signal and the physical port can be defined to only use the specified indices. If no indices are specified, then the whole port is used. The other bus interfaces are similarly mapped. The bus interfaces for external memory will contain different interface modes. The interface mode can be changed here, as well as in the bus interface editor. Changing the mode changes the mode-specific part of this editor. A target interface can be attached to a memory map, or to an initiator interface through a transparent bridge. A system interface is used for bus types that do not fit into the initiator or target category. A system bus needs a system group. This is selected from the available system groups of the used bus definition. A channel is used in a bus component to describe which bus interfaces are internally connected. Therefore, we will use a partly completed bus component to demonstrate them. Channels are constructed from bus interfaces with mirrored initiator and target modes. Mirrored initiator bus interfaces do not have mode-specific options. Mirrored target bus interfaces may contain additional address information in the form of a remap address and range. Remap address defines an address offset for the target bus interface connected to this interface. Remap address is optional, but if defined, range becomes mandatory. Range defines the address range available for the connected target bus interface. A channel needs at least 2 interfaces, but multiple interfaces can be selected. If multiple interfaces are used in creating a channel, then an internal connection is created for every possible pairing of a mirrored initiator and a mirrored target. CPUs are the programmable cores of the component. A CPU contains addressable space described by range and width, mapped to the selected memory map. This component does not have any memory maps, so we will create some example maps. A memory map may contain subspace maps, which can be connected to an initiator interface to create a global memory map for the programmable core. The referenced memory map is mapped to the addressable space. The available range of the memory map can be seen on the right. The addressable space of a CPU can be divided into regions. The regions are shown in the same image as the memory map, displaying the accessible memory area. When changes are made to the regions, changes in the placement can be observed in the image. Thank you for watching this video. For more information on Cactus 2, please see the other tutorials, or visit our GitHub page.